Well, good afternoon. 15 minutes. It's going to be a bit of fun. All right, so I'm going to talk about future-proofing data centers. Obviously, this is, as PTC has evolved, obviously a lot of the terrestrial networks have come in. Data centers is a huge part of our industry. So if you think about how data centers have developed, think all the way back when the first rooms that were developed for the first compute systems, they were very much like this. Oh, that's a terrible picture. They were really designed for people. So all the ASHRAE standards we have are based on those people standards. So look, everything's the same. You've got a raised floor plenum, you've got a drop ceiling plenum, and things really haven't changed that much since then. As we've evolved and as systems have become much more diverse and we've started building discrete buildings for data centers, we've used a lot of that same supply chain. Because this was here, this is the way it was, this is the way we've been building. And as we've moved from mini computers to server systems, again, we looked at supply chain, and we looked at racked systems, and we used the same methodology that AT&T developed in the 20s when they started developing 19-inch racks. So a lot of what we have today is based on existing supply chain and the way we do things, which has been fine for the most part. As industry has moved, as we've moved more from client server to more of web-based systems, those things have been perfectly adequate, and we've built data centers all over the planet. But as those systems are starting to change, we've had to start to rethink how we develop those physical infrastructure buildings. So going back, let's look at just watts per square foot. So in the old, when we had mainframes, even mini systems, and the first wave of cloud-based applications, really we were looking at about 100 up to 150 watts per square foot for cooling. And if you think about, if you're involved in data centers or you're procuring data centers, it's all about the cooling. Bringing energy, electrons into a building is just a function of doing a deal with someone and trenching and buying transformers ahead of the game, but it's all about cooling the infrastructure you have in there. So 150, that was pretty adequate for the most part. If you look at what the hyperscalers are doing now and really pushing the envelope, we're up to about 300 watts per square foot. And that's a nicely defined architecture, but it's a prescriptive set of architecture. Typically, the hottest gear is in the middle, and then you move further out to the edge. We have down to 3 kilowatts, just to balance that load based on fluid dynamics of underfloor cooling and all of that. As we move further up the stack, if we're thinking about the new chipsets that are coming out from NVIDIA and Intel, the converged architectures that are being built, we're really pushing the envelope in terms of the capacity that we want to deliver as a piece of equipment in a building to develop and host the services and platforms that our customers are looking for. So the modern IT, we're not even touching up into the AR, MR. And you can talk about whether it's edge or core, and that's a whole other argument, and we can talk about that. But my philosophy of the edge has always been, it's the lowest latency point between a service and the consumption of a service. So depending on what those two things are, really dictates how big that service engine has to be and what the device is. So if you're looking at just streaming content to a phone, it could be at a CRAN, it could be at a very small CO in a building. But if you're looking at developing and delivering platforms like Azure or Office 365, then those edges could be up to 20, 40 megawatts, but they're just in the market and delivered over whatever methodologies are appropriate. And the previous speaker talked a lot about 5G. I'm not going to go into that, although that seems to be the buzzwords and whatever. Anyway, so it really depends on what you're delivering, but what we're seeing is a dramatic shift in the technology, the ability to condense the technology. Once you get into virtualization and consolidated and converged architecture, we're seeing that our customers are requiring a lot more power delivered to the rack, which requires a lot more cooling, and so on and so forth. And we haven't even touched on the spikes in demand, the new technologies that are coming out, and the increasing complexity. So we're getting way up there to 50 kilowatts and beyond. Now, that can go, you can start talking about, there's a lot of talk about emerging or submerging the architecture in mineral oils and having that submerged cooling architectures, which is all well and good for very specific use cases, maybe a GPU-based architecture, but it's very messy to work on. There's still a lot of dispute as to, even though it's a non-conductive mineral, what's it actually doing to the cables and whatever that's submerged in there, and it's horribly expensive and very heavy. So air is always good. But I'm trying to keep to time here. if you look at a traditional legacy data center, I mean, this is a hyperscaler. You can see that, raised floor, underfloor cooling, the cracks down the side, we've got a hot aisle containment, and this is a very well-designed site. So it's a 5 megawatt data hall, it's about 22,000 square feet, 50 cracks down the side, and if you get those just right, 5 minutes, wow, that went quick. If you get that just right, you can probably get about 200, 230 watts per square foot of cooling. There's no expansion capability whatsoever here. So as technology churns and as the customer says, okay, and now I'm going to use the latest chipsets, I'm going to use the new servers, I'm going to build my own with Foxconn, I'm going to use whatever. They're really stuck there. They could transition their technology, but they're going to have to do exotic things like with underfloor dams to move that air to the center. It's just, it's challenging. But from a data center provider, that's fine because you have to buy another hall. But obviously customers are getting wise to that. So it's time for an adaptable data center. And so here you can see it's a no raised floor, which a lot of new customers are very happy about. They're doing their rack and stack and their burn-in off-site, just rolling those in, these incredibly heavy cabinets, fully laden, and they just plug them in. You can't really do that with raised floor. You've got to do, put down melamine, you crack the floor tiles, it's horribly expensive. Now this particular one, this is designed as a 4 megawatt data hall. It's less than 8,000 square feet. But because of the cooling system here, which is, the PU is much, much lower, so that's energy cost, that's all that savings. We're looking at twice the capacity in terms of watts per square foot. But also, there are provisions here where you could put another 6 of those cooling devices in there, which brings you up to 3 times the cooling capacity in this data hall. So that's what we think customers are looking for. They're not quite sure how they're developing. Unless you're a hyperscaler and you're not just dropping down one of your existing nodes, you're going to put network gear in first, then you're going to see how it goes in that market, you're going to start ramping very quickly. You need the ability to be flexible, to grow on demand, to expand on demand, to actually take use of the infrastructure that you put in place for the networking, the operational costs, the CapEx, all of those hidden costs that the providers are looking for to offset. So I'm conscious of time here, so the technology that is going to be prevalent going forward is the ability to mix and match those cooling architectures. So you have the ability to start small, grow on demand in chunks and as the business requires. So I'm coming to an end, so you've got to rethink the data center more as a data center factory. Throw out all the preconceived ideas, look at what's out there, rethink the whole infrastructure. And what I will leave you with is this equation. So for those of you who know this, and just say no to crack. So I was going to do a whole reveal here, so let me just... Okay, here we go. Let's just go for the whole thing. There we go. All right. So this is something we feel very strongly about. Just say no to crack. So obviously this is second law of thermodynamics. In fact, let me just do the next reveal here. There we go. So the amount of energy required, it's the mass flow equation, it's the air pressure, and the delta T. The delta T is the critical part. If you think about cracks, when you move airflow across something, typically you can do a state change of temperature of about 4 degrees. What you need using this and using physics as opposed to just mass of force of air, we can get about 45 degrees of state change. So it radically changes the game. Anyway, I think that's my time. And anyone who wants it? Oh, keep going. Okay, I'll do my boxer shorts as well. Okay, and I've got shirts for people who want them. You just shout out and grab them. But any questions? Any questions? Wow, that's the fastest pitch I've ever done. Well, not pitch, informative discussion. Yes. Any questions? Yes, sir. Oh, great question. So we see them, there's a lot of, there's a good question. We have a Fortune 500 who, they used one of our sites as a backup. They're in an existing now the second largest, based on everyone keeps buying everybody else, second largest REIT on the planet. We were their second, basically their DR, but they found they could put so much within our rack systems, and these are like the 9-foot racks. They're pulling down 37 kilowatts each rack. They do a lot of the back-end transactions for a lot of the travel companies. So much so that they wanted to revamp their primary, but to do that, they had to put rear-door heat exchangers on every one of those cabinets and pay for that. The REIT wanted them to pay for it. So now we're the primary, and they're just moving everything out, which is great. Yes, sir.
So I'm from Alaska.
Mm-hmm.
We have a lot of free cooling.
Yes.
I'm curious as to how far the engineering has gone to capture free cooling numbers.
Sure. Yeah. Oh, absolutely. And there are challenges. So a friend of mine built a data center for a large social media company in Norway. Lots of hydro, almost free energy, and very, very cold. But because the air is so dry, they had to put, they basically put humidifiers in the vents, but they were making snow. Because, that's a snow machine. When you have cold, dry air yeah. So they had to rethink that whole element. Now, we can use free air cooling. There's a lot of that. But then you've got to look at particulates. There's lots of extra things that have to come into play. I mean, Yahoo had, I think they called it their chicken coop methodology, and Amazon have tried some of those things in those sort of areas. For those customers, they don't really care because the technology is a commodity. They just switch it out. If something fails, they throw it away. And, their business is, they make enormous amounts of money, so that's not an issue. But for most businesses, they're looking at a 3-year depreciation of assets, so they have to think about what they're doing.